So our second speaker is Larry Melling of Cadence. Larry is Director for Product Management and Marketing at Cadence Design Systems. He's responsible for software-driven verification, virtual prototyping, and embedded software debug. And he's going to talk about achieving real verification reuse from a software-driven point of view.
Good afternoon. Can I be heard okay?
Yes, you can. Thank you.
Okay, great. All right. So I'm going to give you a view of how Cadence has tackled the same issue of SOC level verification. And just first kind of looking at this from a historical perspective of what's been going on in dynamic verification over the past several decades. That was the concept of doing directed testing, and this was proving to be a real issue in that the challenge of getting the chips or getting the designs verified became larger and larger, and following a directed approach, nobody was able to really be sure when they were done. And then along came the HVL coverage-driven verification model and era, and the use of constrained random and metric-driven verification. And this proved to be very, very effective and gave us an ability to predict when we would be finished with our verification job, especially at the IP and block level. But what was found by people using the HVLs is that as you moved up to the system level, that it was not sufficient to be able to do SOC level testing. And at the SOC level test, you also wanted to get back to some of the directed some of the directed concept, because a lot of SOC verification isn't about verifying everything that the SOC can do, but more about verifying the use cases of how the SOC is going to be applied. And so this is kind of the era that we refer to as software-driven verification era, looking at SOC top-down use case level testing, automatic or automated constrained random generation of software tests. Obviously, maintaining what we've learned from the value of coverage metrics and wanting to apply the concept of coverage metrics at this SOC and system level, and then the ability to reuse all of those tests across the many platforms that have to be utilized during the process, from simulation, emulation, prototyping into post-silicon, as we've been talking about. So why is this? I mean, I think Anand showed a similar picture here. The concept is an SOC, modern SOC is many IPs, that are involved in the system. Obviously, many cores, both symmetric and asymmetric, and homogeneous and heterogeneous types of cores, as well as lots of software that gets applied to not only provide application capabilities, but also for some of the accelerators and things that you use inside of your devices, there's actual functional software that must be there to provide the functionality that's required. Some of the gaps that have occurred at the SOC level is really this concept of how to develop are being used today. They're more directed, and as you get into this multi-core, multi-cluster type of environment, they're more complicated to develop. So it's, in many respects, it's like a parallel programming problem. So it's not a simple problem that can just be, sit somebody down for a short period of time and have them, create a full suite of directed tests. The programming is somewhat complicated. There's a lot of coordination that needs to go on, and as a consequence, bare metal testing has really been limited to what I would call more integration level testing and kind of proof of life testing that most customers do, where they're going out and just verifying that, oh, I can, turn on these different pieces of IP. The IP can talk to each other, in the system, and those kinds of operations. Throw on top that Adnan was just talking about, as well as overlay that with concurrency and power, and you have a very difficult programming challenge. So what a lot of people have done in that, facing those problems, is to move to a pure functional sort of view of saying, okay, well, I can't write all these tests, so I'm just going to run my operating system and run some application tests on top of my operating system and kind of, prove out that my SoC is going to operate under the working conditions that it's going to see, in actual application, which is, a reasonable approach, to at least getting to the point of the use cases that are going to be seen by the SoC. The big side effect here is that once you throw in a complex OS, your debug problem becomes significant. So once you find a problem or uncover a problem, the finding it and fixing it becomes a much bigger problem. Then obviously, how do I measure what I've tested? Using an OS and that sort of an approach, you can't really apply metrics very effectively to understand how much you've tested and what kind of things you've done over that space. As an example, what Adnan was talking about over the Coherency protocol space. How many of those transitions have occurred? How many have occurred across coherent processors? So I reuse the test developed from the IP to the system level. This is a common problem of bringing in IP, adding it to the system, and wanting to apply system-level tests to make sure that that IP stays functioning. The most common of these is power management. So your SoC has a power management protocol to it, and you bring in a new piece of IP, and that IP has to operate across the different power domains and transitions. And as a consequence, you want to test that IP, not to retest all the work that you've done at the IP level, but to really validate that the IP stayed operational across these system-level states. Then how do I develop the tests that work on all the validation platforms? As we talked about, there will be configuration issues and things that need to be adjusted for platforms, and so this is one of the areas that people are also looking for solutions in. How do I get that information transmitted such that I can get tests across all these platforms? And then finally, what tests to develop? That's another big issue, because as we pointed out, these system-level spaces, the number of different are significant and can lead to a large number of tests. So, what tests do I develop? Today's approach is as opposed to testing toward a coverage goal or testing toward some other defined set of parameters, where the testing technology, what we'd really like is the testing technology to help us get there, like we're used to with the HVL approach, and constrained random helping us progress toward some coverage. And then the last piece of that is kind of back to why the HVLs are not sufficient at the SoC level, is we really want to drive tests from a legal use cases perspective, because as you get to the SoC level, the number of illegal kind of test cases becomes larger, and if you spend a lot of time generating tests that are extend your verification time any longer than is necessary. So as we've been talking about, and one of the things that the Portable Stimulus Working Group is looking at is really what we do about SOC level verification and what are the verification and validation requirements. And there's there's really three axes to what we're looking to do in the group that have been identified in the requirements leading up to the formation of the working group. The first is, how do we communicate and share use cases between users? How do I, let my, experts in power management describe use cases that fully exercises the, legal, power states and transitions of the system, and then be able to hand that off to the people that understand what the coherency capabilities are of the system and capture the use cases around coherency and communicate those between those different users. Because often those different users speak different languages. From the verification engineer who's a UVM-versed system Verilog kind of engineer to the software developer who is writing directed tests for doing integration level testing, who is a C programmer. And how do I work with those different types of engineers and allow them to really share information and reuse information across the different groups. The next one is that vertical reuse that we talked about, is how to create and reuse the use cases from the IP to the SOC level and on up into the full system level of software running on top of the hardware. And then the last but not least is the horizontal reuse, the moving across the different platforms from virtual platforms, all the way out to the post-silicon. How do you use tests and be able to execute those tests across those platforms, but not only execute those tests across the platforms. One of the goals is to execute them natively, so you can take advantage of the performance of the faster platforms, and as you get to higher performance platforms, to be able to expand the testing to take advantage of the ability to run more cycles as well. So the solution that Cadence has created for this is our Perspec system verifier, and it's slightly different in its approach in that it's a model-based approach. Although we do have a model-based approach that has a visual representation that is aimed to be easy to use and reuse, and we'll talk about that in more detail. And part of one of the key capabilities of the Perspec system verifier is the ability to take this abstract model that you capture and that reusable form and exercise it via a set of powerful solvers that allows us to come up with different solutions to an abstract set of goals that you want to accomplish in your tests, and then be able to generate C tests for those. And then those C tests are obviously making use of a a verification OS, if you will, that has scheduling, inter-process communication, runtime randomization kind of capabilities built in, so that those can be exercised in the tests. This gives you a quick view of what the flow of that we follow is. Okay, you start with the user defining their use case. And that use case is captured in an abstract form, so it's done by capturing the actions and resources of your SOC. And so it is done at an abstract level, so the modeling is not too onerous, yet it's sufficient to allow for us to apply some formal solver technologies to it. Now what happens is we take that abstract use case and the solver gets applied and it comes up with a set of concrete solutions that would fulfill that use case. And I'll show some more about what that looks like in real life in some subsequent slides here. So those concrete solutions can be in turn generated into C-tests. The C-tests can be executed on the different platforms, and then the results of those C-tests can be used in that same abstract form for debug and analysis. So you can look at your coverage, you can look at the actual execution that occurred of the test and go in and debug it at the abstract diagram level or down into the detailed C software debug kind of level. Before I get into giving you some more details about how that works, I would like to just, this is a recent presentation done at DVCON by ST, who's one of our early users of Perspec System Verifier. And in this case, they were using it for that vertical reuse kind of capability where they were applying it to a GPU piece of IP and applying that to make sure that the GPU stayed functioning across their complex power system. And this just kind of highlights some of the capabilities that were valuable to them in the process, and some of the results that they saw in terms of productivity of creating tests, and also kind of the number of tests that they were able to achieve using automation, to achieve that full coverage that they were looking for, and where they were in the manual versus where they got to with automation. So let's take a closer look at what we're doing and what we mean by use cases and how this all comes together. This is kind of a a simple view of what a use case can be about. A use case can come from a product perspective, or it can come from an architectural perspective. In this case, we're talking from a product perspective that, oh, I'm developing a mobile chip. I want that mobile chip to be able to view a video while it's uploading it. And so I can capture that use case very simply in language, but we want to be able to also capture it in the tool. And in this case, in our tool, what we would do is we would describe the capabilities, the actions that the SOC has available to it, and the resources that it has to use, and we would capture those models to say, okay, well, the modem can do a transmit and a receive. And so the ability to upload a video would require that I be able to transmit that video. The video itself, I want to decode to a display, and that gives me the ability to view that video once I decode it to a display. And in this world, what we're using is a UML type of annotation to describe these actions shown here in these green boxes, the transmit and decode. We couple those two together to say we want those to occur at the same time, and it automatically fills in what resources are going to be needed to be able to do that, to pull that video from a memory buffer and to create a video stream for the display. Now, I can go in and say, well, I want to take that to another level where I actually want to describe something more specific, to take a video buffer, convert it to MPEG-4 with medium resolution, then transmit it through the modem via any communications processor in parallel, and and basically go through and describe more detail. So this is what that abstract use case would be. So again, it's still not a complete concrete scenario that can be executed, but it does, describe in more detail what kind of tests that I would like to run. Then in our system, what we do is we can take those abstract use cases, use the solver to actually create the concrete solution or a set of concrete solutions that will satisfy the particular goals that were articulated in the abstract model. Okay. So in this one you'll see that we were able, these blue boxes, these blue actions were what was added in by the solver, and said, oh, well, to get a video into the buffer, I have to get it from somewhere. So it randomly picked that, oh, I'm going to grab the video buffer from an actual camera in the system. And now I get the video captured into the system, and then I convert the format, and then I put in, set up a parallel operation to do transmit, decode to display, and show it on a display, which is another action that has been added. Here you see it go through and choose the, filling out all the details of the formats and to make it an actual test case that can be then generated and executed. Okay. So this next section kind of is there'll be some repetition, but just looking at the same kind of concept of going after a coherency verification and looking at how that is accomplished in the system. The first thing, one of the things that we talked about was identifying what the CPU subsystem is going to look like. So in this case, you identify all the cores, what clusters are associated with the cores, and what the what the cacheability of the core is, and any ID information. Then we go into the resources of what memories are available and what address ranges those are covered, and then we go into the memory access indirection register settings, to get those set up, and then also the default page tables, as Adnan was talking about, the whole DVM kind of configuration capabilities that need to be set as well. Okay. So this is where the user comes in and in a table form basically provides all this information, gets it all set up, and then that can be used in going out and actually doing the cache testing. So in coherency, again, there's kind of two sides of it. There's the cache coherency, the ability to for the different processors and their to share cache amongst themselves, as well as I/O coherency, where we're looking for the I/Os to be able to snoop cache information from from the processors, and not have to go back to memory to get the information that they're looking for as well. So as I said, so this is that same state diagram, looking at the MOESI Protocol, looking at all the different transitions that can occur, and in our environment, how this is captured is through this model, as we talked about. It's a system-level notation. The transitions that of the states we're talking about are actions, and the states themselves are tokens, that are passed, so we know, what the current, position of where we are in the state diagram. The constraints are then written such that you can, naturally describe that state diagram and configure the number of processors. And this just gives kind of an example of, setting the constraint to show what the previous state value was, and how to get to the next state value under a cache hit situation, under a cache miss situation, and then the snoop that happens if a miss occurs. Now what that results in is now I can write a abstract scenario that says, oh, my goal is to write to a cache line when it's in a shared state. Okay. And I can just take that simple goal and then apply this solver technology to come up with view solution to that, where it comes up with, in this case, we're just looking at the scheduling view that looks at the different operations that are going to occur. And again, reading these UML activity diagrams, the parallel transaction bar is basically saying we're waiting until we can start up both of these activities at the same time. And so you see those moving through there. And then this shows you the actual control flow view of the test, the test scenario that shows you not only the actions but also the resources and the caches that are involved in kind of the current states of those caches. So you'll see the shared state you'll see here, the invalid state, and moving through the different state transitions. Similarly, we can do a scenario goal to observe any state from core 1 in parallel to any state in core 2, solve that, and now you get a view of the solution of coming up with many solutions. So in this case, you see, oops, I go back here, we're actually telling it to fill in all the cache states. So we're not, forcing a particular cache state, but saying we want a complete view, and it comes up with all the solutions to be able to, verify all the different legal states. And the states that are shown here in red are the ones that are illegal. So it gives you a complete solution based upon, what are the legal states, and shows you what are the illegal states as well. And then it can give you a during generation kind of coverage view of, okay, the tests that I'm going to generate are going to give you this kind of coverage. And, it'll highlight the areas where, illegal states combinations are shown and obviously shown as zero coverage. Then those can be removed as, unreachable once you've analyzed them and determined that they are, in fact, illegal and uninteresting. And for interest of time, I won't go into each one of these, but you're getting the idea that basically these activity diagrams give you a very abstract view of kind of what's going on in the test, and we also utilize these in debug as well. Now, what's interesting about this approach and the UML kind of diagram approach is that we can really allow you to do better use case reuse. So I can take my use case created by the coherency expert, by the power shutdown expert, and combine those two to create a scenario where I can go through and say, oh, I'm using 3 processors doing sharing cache line and doing cache transactions on those 3 processors, power down 2 processors, continue with the 3rd processor doing cache transactions, power back up the 2 processors, and then validate that the 3 processors can again share that cache line. So this gives you an idea of kind of what the capabilities are, and tackling some of the same kind of issues that Anand was referring to from a slightly different perspective. And obviously, the ability to generate the tests and target those tests toward the platform. So that's really, in summary, it's kind of, about, these tools are about generating, giving you more productivity through the ability to generate tests, but also not only generate tests, but to generate tests that are more complex than you would be able to generate by hand. The abstraction gives you an ability to really understand the tests and debug them and get to root cause of issues much faster. Automation obviously gives you more productivity and the ability to generate the tests. And then the portability across platforms and the ability to measure the SOC level coverage metrics for those tests. And with that, I'll close off. Thank you.